you remember on Thursday, I kind of traced out the whole triangle and then traced out one of these smaller ones. And I said, okay, looking at the black triangle, where's the right angle? And you would have told me it's angle C, right? Okay, let's do that in black. You would tell me it was angle C in the black triangle. If I asked you in the blue triangle, you told me it was angle D. And then we said that they both shared angle A completely. So then A would have to be in the same spot as well, right? If I'm looking at the black one, the remaining angle in the black one that I haven't talked about would be angle B. And in the blue one, the angle that I have not talked about, so I've used D and A, I did not talk about C. So I have to name it triangle CAB and triangle DAC. Now, neither of these names are over here, but if I go through and look at, if I go A to D to C, that's that name right there, and start at A and go to C and then come back to B, that's that name right there, correct? Okay, so this demonstration here in GeoGebra is showing how we went through it by matching right angle to right angle and then reflexive angle to reflexive angle and get a triangle similarity. GeoGebra actually takes the images, separates them, rotates them, and flips them so that you can see a one-to-one correspondence with angles. Regardless, though, each way we do this, we get AD compares to AC. Okay, then we get DC compares to CB. And then we get AC compares to AB. And right here, that one and that one, it's terrible, you can't see it very well. That one there and that one there, would you agree that AC is a repeating component in both ratios? Okay, so every time we should do this, we should see no other segment repeats. So if I go look at like AD doesn't repeat in any of these ratios again. If I look at DC doesn't repeat in any of these ratios again. Okay, CB doesn't repeat in any of these ratios again. Okay, but each one of these similarity statements, we find out that there is repetition with one segment. So if I go looking at the ratios here, AD compared to CD, we go DC compared to DB, and then we go AC compared to CB. And again, the repetition is that one and that one, CD or DC, however you want to write it. But AD doesn't repeat again, DB doesn't repeat at all, AC doesn't repeat, and CB doesn't repeat. Does that make sense? Okay. And then in the final one, AC compares to CD, CB to DB, and then AB to CB. And again here, CB is the one that repeats. Okay, no more ACs. AC only one time, CD only one time, DB only one time, and AB only one time. So every single one of these relationships gets a repetition of one of the segments. And the segment that's repeating every single time, going back to the original triangle, which is this one. I'll just put a star on there. That's the original triangle. AC is an altitude. That's one of the repeats. CD. Let's see here. Oh, I'm sorry. So CD is that one right there. That's the altitude. It's over here. Okay? That's a repeat. And then down here, CB is the other altitude. That's the repeat. So what we're seeing is that the term that is repeating in two of the three ratios in each one of these similar triangles is always one of the altitudes of the original right triangle. Does that make sense? Everybody see that? Now, what goes in the other parts? Okay, so if I'm just looking at that ratio right there, so AC was that distance right there. Okay, AD, so D is right there. AD is that right there, and AB is that right there. Okay, would you guys agree that AB, this longer distance, which is that ratio or that component right there, would you agree that's the hypotenuse of the original triangle? Okay. Would you agree that this here, can I refer to that distance right there as a portion of the hypotenuse? And is that portion touching or shares an endpoint with the height or the altitude that we chose? Okay. Keep that in mind. And we haven't talked about that yet, but there's a theorem that goes with that. Let's go with the other leg. The other leg was CB. Okay. If I look at the other two parts, so now we're looking at just those two ratios, would you agree that AB is that entire hypotenuse? And DB, so D was right there, is the part of that hypotenuse that is touching the altitude that we chose or the leg we chose? That makes sense? That ratio and that, or that proportion up top and the proportion on the bottom are really the same format. Okay, and we'll talk about that in more detail either today or tomorrow. This one in the middle, this one's the easiest one. This is the one that my video on Friday was trying to get you to recognize. And what this says is that DC, well, this is the altitude that is on the interior of your triangle. Okay? The other two parts that fill in these spots are that distance there and that distance there. They're the two portions of the hypotenuse that are created by that point D. And they always go in those two spots. Does that make sense? So on the video, let's see here. We came down to, first we talked about this. These are means. Okay? And when they're the same term, which is what we were seeing right here, AC and AC, CD and CD, CB and CB, when they're the same term, we rename them and call them geometric means. See, they're X and X. Okay? So we say that those are the geometric mean between A and B. And all that means to us, the phrase geometric means tells us that the things that go in those two spots are identical. Okay? Those are the means location, right? When we talk about the word geometric, a lot of times the word geometric, like you're talking about sequences and series, means ratio, means that we're multiplying. Okay? But this theorem, all this theorem says if the altitude is drawn to the hypotenuse of a right triangle, then two triangles formed are similar to the original triangle and to each other. That's exactly what that demonstration was in GeoGebra. Okay? Now, it's very hard with a static picture for you to take this green triangle and reflect it and rotate it and align it so that it matches up exactly with the blue one, and then take the overall one and do the exact same thing. So right angles match up correspondingly with right angles, and then acute angles with acute angles. That's hard to do. Okay? These are the three similar triangles that get created. Okay? Using the transitive property, we can just align them all in order. ABD, congruent to DBC, congruent to ADC. Now, obviously that changes if I change the letters, right? Okay, sometimes you'll see this problem with, instead of A, B, D, and C, they might use S, R, T, and U. All right, so you have to understand the structure of how to do this instead of just memorizing these letters in this order. Okay, but that got us to this corollary. So if any of this stuff does not kind of make sense, Okay? If it doesn't make sense, are you not going to be able to do what we're doing? No, you should still be able to follow along and do what we're doing. But if it makes sense, what we're doing will be so much easier. Okay? So, there are, like I said, the video from Thursday, the video I signed on Friday, those all explain how we go through this, again, plus what we just talked about a few minutes ago. This is what it's called a corollary. It comes from the idea that the previous theorem really establishes this, and it's exactly what we talked about with this distance right here. It says when the altitude is drawn to the hypotenuse of a right triangle. So that's what we've got going on here, because this segment right there, okay, DB, is the altitude drawn to the hypotenuse of a right triangle. So we know that's occurring, okay? If that's the case, then the length of the altitude, which is DB here, that is the geometric mean. And by definition, geometric means go in those two spots. So saying DB and DB should go in those two spots. And now it says it is the geometric mean between the segments of the hypotenuse. Well, B creates two segments in my hypotenuse. It creates that distance, and it creates that distance. You guys agree with that? Those then are what go in the remaining spots, AB and BC. Is that okay with everybody? Now, generating that was fast. Okay, I want to go through this real quick and show you that if we didn't have this corollary, what we would have to do. If we didn't have that corollary, we would have to say, okay, green triangle, blue triangle, and overall triangle. Those are what I'm going to refer to. Let's say the overall triangle is triangle ADC. Okay, let's say that is similar to triangle. So would you guys agree that, so again, this green one, what angle does the green one and the overall one, which angle do they share in their entirety? Angle A. So A was first here, so A's got to be first there. Okay? Now, D in the overall triangle was a right angle, correct? What is a right angle in the green one? B. And so this one here, that's AB so far, I'm trying to name the green triangle. So then letter D would be the last option, right? Okay. We'll do the same thing for the blue one. Again, triangle A, D, C is the overall one. Okay. Now, this blue one, which angle does it share with the overall triangle in its entirety? Look at this blue triangle and the overall triangle. Which angle do they share completely? Angle C. So C is the last one there, so I'm going to come down here and put it last there. Which angle in the overall one was the right angle? D. Which one's the right angle in the blue one? B. So D and B need to be in the same spot. And then what angle is left over for this blue one? D. Okay. Now, because of the transitive property, the third argument that we can make is that those two triangles are congruent. So triangle ABD are not congruent, similar. ABD similar to triangle DBC. Okay? So now running through this, if those are similar, we should have some ratios. We should be able to say AD compares to AB, just like we can say DC compares to BD, like we could say AC compares to AD. Over here, we can say AD compares to DB, DC to BC, AC to DC, and this last one, AB to DB. BD to BC, and then AD to AC. Okay? Look through those ratios. Does this exist anywhere? It's right there, correct? Which route would you rather take to generate? So this is going to be true all the time. Which route would you rather take to generate that? Would you rather go this route here? Or would you rather say, okay, if I could take this altitude, that is going to be then the geometric mean, so it goes there and there, between that part and that part, right? So every single time that we have this scenario, we have this triangle, this right triangle with the altitude drawn to the hypotenuse, that ratio, highlighted in green, is going to show up in one of those three extended ratios on the bottom. So instead of writing all those out every single problem we come across, if I gave you, I don't know how many questions, I give you 10 questions in homework, you wouldn't want to do this one time, let alone 10 times, right? Okay. So if we can use this corollary, it allows us to get to that conclusion much faster. So that's kind of the approach that we're taking here. So what's that allow us to do? That if I can find out these distances, or if they provide me with some of these distances, we should then be able to find missing values. Okay, so here it says in triangle PQR, RS equals 3, QS equals 14, find PS. Okay, so triangle PQR, is that a right triangle? Okay, is PS an altitude drawn to the hypotenuse? Yes. Okay, that's key. Okay, one of the things that happens in either the next section or the next chapter, I think it's the next chapter, is I give you a picture like this on a test, and I ask you to work through it. That's a Pythagorean theorem question, and I ask you to work through it. Is this the picture of an altitude drawn from the right angle to the hypotenuse? Is that a right angle right there? You don't know, right? Okay, so it might be, but we don't know. So that if we don't know, we can't guarantee that the process that we're going through right now will work for it. So you need to be told that this is a right angle there. Okay, so just keep that in mind. So we have the conditions that are needed. I'm going to go through and plug in the information they provide us. They say that you know RS, so you know that distance right there is 3. You know that QS is that distance there is 14. Find PS. I'm going to let PS be X. Okay. The previous corollary says that this altitude is the geometric mean. So it goes there, in there. Is that okay with everybody? You will never have anything other than an altitude in those two spots, no matter what we do. You'll always have an altitude. Okay. Now, because it was the altitude that was on the interior, okay, then it's the geometric mean between that part and that part of your hypotenuse. So I'll put a 3 here, and I'll put a 14 there. Okay. So what do I get when I cross multiply here? X squared equal to, I'm just going to write, I don't like, because I know what we're going to do here, I don't like, and I talked about this I think last week a little bit, I don't like multiplying. If I know I'm going to take a square root, I always foreshadow. I'm reading a book, I always think about what's going to happen next. Watching a movie, always going to think about what's happening next, right? Doing math, always going to think 2 or 3 steps ahead before I actually do those steps. I know that if I got x squared, I'm going to have to, because there's no x to the first, I'm going to have to use square roots here to solve for x. Okay? Well, I know that square roots is going to involve, if I'm going to simplify them, it's going to involve factoring, which is division essentially, right? Okay? Finding numbers that multiply together give me a product. I don't want to multiply this out then, because the square root process is actually going to make me undo that eventually. So I'm just going to leave it alone. Does that make sense? Okay. I'm going to square root both sides now to solve for x. Now, because we introduced a square root, That's plus or minus. I get something like that. Okay? Now, because of the laws of exponents, I can rewrite that radical 3 times 14 as radical 3 times radical 14. Okay? Now, what we do with radicals is we try to make sure that if they're a composite number, okay, meaning they're non-prime numbers, okay, is there a largest perfect square that will divide them evenly? Okay, so if I look at 3, 3 is prime, so I'm not going to do this with 3. Okay, I'll do it with 14. 14 is composite. Is there a perfect square that will divide 14 evenly? And the only thing we have to do is check perfect squares that are smaller than half of 14. Because anything that is smaller than half of 14 will generate a quotient greater than 2, which is what I'm looking for here with 14. So I'm looking at 14. Okay, half of it's 7. Perfect squares that are less than 7 are 4 and 1. Do either of those divide 14 evenly? No. Okay, so 3 is simplified, 14 is simplified. What we like to do then is we put them together as one radical. So radical 3 times radical 14 is actually the same thing as radical 42. That's one approach. Okay, I don't think, and I'm just going to make the assumption, I don't know how much you guys got through radicals. In my opinion, even if you had a full year of algebra last year in person, you still don't get through enough radicals to fully work with them efficiently enough to be successful at this level. Okay, so as we go through, I'm going to do them alternative ways. Okay, and the alternative ways really isn't a different technique. It's just using the same rules or same laws of exponents in different orders. A lot of times people will say, okay, I got x squared, 42, right? So you get x squared equals 42. And they square root and they get plus or minus root 42. This is what we had, right? At that stage, you need to make sure that 42 is simplified. So what we do is it's called the prime factorization of 42. We start dividing it by numbers that we know divide it evenly. So 2 and 21. 2 is a prime number, so we stop with that number. We don't continue down dividing that. Okay? But 21 is composite. So we think about numbers that divide 21, 3, and 7, right? Okay? Both those are prime, so we'll stop there. What that tells me is that 42 is the same thing as 2 times 3 times 7. Every composite number like 42 that you ever come across, any number that is not prime, can be rewritten as a product of prime numbers. Okay? Now, if I look at 2 times 3 times 7, any configuration of those values does not yield a perfect square. Okay? So 42 is already simplified. If I look at something like, let's do 84. 84 goes to 2 and 42, right? 42, 2 and 21, 3 and 7, right? So 84 is equivalent to 2 times 2 times 3 times 7, right? 2 squared can look like that, right? Okay, so 84 is the same as that. But now, the square root of 84 is the same as all that. Does that make sense to everybody? What is 2 squared the same as? 2 times 2, which that quantity is 4, right? Is 4 a perfect square? So that means that 4 is the largest perfect square that divides 84. Okay? Can we rewrite this as 2 squared? I can put these underneath their own radical. That's laws of exponents that allows us to do that. Square root and power 2 cancel each other out. You're left with that, which can be rewritten as 2 radical 21. Have we seen that at all in our algebra? No? Show of hands, like, just, I need, because I need to know if we need to go over this further, so show of hands, who has seen that? So we've seen it, we're not comfortable with it. Huh? No, not division. Okay. So we'll work on radicals. All right? Multiple ways of doing it. All right. So this question here, same thing. It's just asking now to put some context to it. Says Mr. Martinez is designing a walkway that must pass over an elevated train. To find the height of the elevated train, he holds the carpenter square. You guys know what a carpenter square is? Okay. Come on. You've seen these before, yes? Okay, manufactured right angles, usually in a certain ratio of this length to that length, probably in a 3 to 4 ratio, so that the hypotenuse is 5. But it's a manufactured right angle. We know it to be a right angle. So he holds that up to eye level, and basically along one of those edges, he makes an imaginary line or cites an imaginary line that goes to the top of the train. The other line goes to the bottom of the train, okay, of this elevated track. It wants us to know, it says find the distance from the street to the top of the train. All right, so how big or how long would this distance right there end up being? 5.5 feet, right? That's the same as the height of the man, okay? What we don't know here, is that distance there, correct? Okay, so let's call that distance our X. Blue is probably not the best choice of color here. So the reason I talk about that carpenter square is because not every problem is going to give you the picture. So you would need to know that a carpenter square is a right angle, right? And now you have an altitude drawn from the right angle perpendicular to the hypotenuse. You know this is 5.5. This is X. Do you know the distance right here? Because it tells me he is 5.5. If this segment right here is horizontal, then we could transfer that 5.5 to that. Huh? Yes. So this is the edge. So this here is the edge of the square. This is the other edge of the square. So he lines this side up with those. Okay. And because of geometry, he doesn't have to know, like that segment right there doesn't have to be drawn. But it is there. It exists as the distance that he is away from the train. And that distance then is, because we measure a distance from a point to a line perpendicularly, we know it exists, and it should be the distance that he is away from that train. That kind of makes sense? So this blue distance is not it's not following the actual segments or part of the square. Okay with that idea? So you got your square, like that would be your square, right? So this red line would be that line of sight. This one here would be that one, okay? And in all actuality, as he's doing this, he doesn't have that line drawn out. but he knows that he's 8.75 feet away from the train. So even though it's not there, he knows what its amount is. Does that make sense? So is that 8.75, is that an altitude? So with the corollary that we just had, it should go there and there. Does that make sense? And then what should go in these two spots? Well, it should be that purple part and this blue part, right? So x and 5.5. So now when I cross multiply, in this case, because I'm not getting an x squared, 5.5x, you can write it this way, 8.75 squared. What would I do to solve for x now? Because that right-hand side is just a number, right? 8.75 squared. Yeah, so this is a 76.5625. I would divide both sides by 5.5, right? And it gives me 13.92. Okay. Now, is that, because I think I heard you say this isn't realistic, like, would that be like the best way to do this? Is that answer going to be extremely accurate and or precise? Probably not, but it's ballparkish, right? So depending on what he needs this distance for, maybe this is applicable or maybe it's not. Does that make sense? So that being said, were there any questions from the homework that I assigned with this that we'd like to talk about? All right, so one thing that I think, and I haven't mentioned this yet, but that is useful because you're going to, tomorrow when we get to the other, there's two other corollaries that we work with here, basically talking about the other segments of a triangle that can be used as geometric means. I like to think about the one we're working with right now. Every single time we look at it, we generate, if we highlight things, what looks like a T, right? A capital T. Does that make sense? Okay. Now whether it's upside down, sideways, whatever, but the base of your T, okay, or the trunk of your T, whatever you want to call it, is going to be your geometric mean. And then the top of your T, the two parts of the top, are going to be your extremes, essentially, in your proportion. Okay? So if I look at x plus 20, that is my geometric mean. That's the altitude drawn from the right angle to the hypotenuse. And then x and 80 should go in the other two spots, right? Now, it doesn't matter where x and 80 go. You can flip-flop them, because when I cross multiply, I still get the same results. So when I cross multiply here, I get x squared. So I'm multiplying these two. I get x squared plus 40x plus 400 equals 80x. Okay, if you miss this problem or struggle with this one, ask yourself if you got that 40x. Because a lot of people get x squared plus 400. But remember, you got to FOIL these two things. Because I'm going to take, so I got x times, so outside times outside gives me x times 20. And then inside times inside gives me 20 times x. And then we add O and I. This is 6. So now that I have an x squared and I have x to the first, we need to factor this. We need to get everything equal to 0. So that means I'm going to subtract 80x from both sides. I get negative 40x plus 400 is equal to 0. What two numbers now will multiply together to give me 40, or sorry, not 40, 400, but add up to give me negative 40? Negative 20, negative 20. So those two numbers can be the same. So negative 20 times negative 20 gives me 400. Negative 20 plus negative 20 gives me negative 40. So then I get x minus 20 equals 0. So x is 20. And I just want to check then, does that make sense? If x is 20, then this would be 20. This would be 40. Those distances are okay. They're acceptable. And now let's just ask this question. If that's 40 and that's 40, and this is 20 and that's 80, what's 40 times 40? What's 4 times 4? 16. So 40 times 40 is 1600. Because I got x to be 20. I was just plugging back in, checking. So I multiply those two and I get 1600. What's 20 times 80? 1600 again. Okay, so that tells me that x was correct. The one thing that is of issue in this problem, and we've talked about this before, geometry, and really every class beyond this other than Algebra 2, the hard part about those courses is the algebra that exists, because the algebra for every problem can be completely different. Okay? And that's just something that we have to be aware of. Okay, and understand the different ways that we can solve equations that might generate. So that's question 6. Any other questions in that assignment? 15? Yes. Yes. What perfect square divides 12? So 4, and what's that give you when you divide it? Yeah. Okay, so you got 4 and 3 like that, right? So what's the square root of 4? So the architect's side view drawing of a salt box style house shows a post that supports the roof edge, a roof ridge. So the support post is 12 feet tall. The distance from the front of the house to the support post is less than the distance from the post to the back of the house. That's key for this problem, because you get two answers here. And this tells us which of those two answers to choose. So if you're missing this consistently, that might be why. Says how far from the front of the house is the support post position? Okay. So it just depends on how you want. Do you want X to be, when we're done, do we want X to be the answer to this question, or do we want to do more to this thing once we have our value from the problem? So you just got to be careful when you're done on how you labeled these parts of this triangle. But my hope is that you guys can see that this problem is giving context to the right triangle situation that we've been dealing with. There's your right triangle, correct? Would you agree that this segment here is an altitude drawn from the right angle to the hypotenuse? Okay. That's the support. It says the distance from the So they tell you that is 12 feet tall, right? The support post is 12 feet tall. So that they give us. Okay. Now, they're looking for, or we need to determine those two distances right there. Is that okay with everybody? All right. They total 40 feet, right? But we don't know what either one of them individually is. So what could I call one of them? X. And this is where you just have to pay attention. Because if you put X right there, this would be 40 minus X, correct? Okay. Here it says, how far from the front of the house is a support post position? Well, here's the front of the house, right? So if I put X there, then I answer with X when I'm done. Does that make sense to everybody? But some of you may have, which is perfectly fine, you may have called this distance X. So this would be 40 minus X, correct? So when I answer the question, I can't answer with X, right? I have to answer with 40 minus X. Okay? But regardless, however you label them, you should still set up the same proportion. The 12 is the geometric mean between 40 minus X and X. So you get 40X minus X squared equals 144, right? Cross multiply. I'm going to rewrite this as X squared minus 40X plus 144. Just going to move everything over with the 144. Two numbers that multiply together give me 144, but add up to 40. They're both going to be negative, right? Okay, so 12 and 12 gives me 144. What's 144 divided by 24? 6. So that's there now. No, because I added X squared here. So I add it to the right. I subtracted 40X. Subtracted 40X. I moved all this stuff to that side. If you, just to give you maybe some help with this, if you're a person that struggles finding, you guys don't use this calculator, do you? So if you have, let's go, you all have Excel on your computer. If you fill in the first column with integers, so 1, 2, 3, 4, and you can cut and paste those. And now in the second column, I'm just going to hit equals, and then my number that I want, so 144. I'm going to divide that by what's in that first spot. Hit enter. So it gives me 144 divided by 1. This one's going to give me 144 divided by 2. So I'll zoom in on this. View. 144 divided by 2. So this gives me my factors, right? Do those two add up to 40? So I'm looking at X minus 36 and X minus 4. Oh. So then we're looking at X equals 36 and X equals 4. Okay. Now just be cautious. Okay. How did we answer? We answered this as X, right? That's how we wrote it. Okay. So when I plug in X to be 36, this distance would be 4. But if I used X to be 4, this distance would be 36, right? Does that make sense? But it tells you that this distance is the shorter of the two. So it wants the 4. Does that make sense? Okay. Basically what's happening here is these two answers are kind of giving that potential, that the roof ridge is actually over on this side of the house instead of on this side of the house. Keep working on that. See you guys tomorrow.